Okay, good morning. I would like to talk about luminosity in electron-positron linear colliders. As you can see from the logo here, this will also be about both warm and cold machines. This is a cold-warm hybrid which was invented at Snowmass. I would like to say that most of what I will present here is a work done by other people in the linear collider groups working worldwide, and I'm not giving accurate account to all the single contributions to this during my talk, so I want to make an acknowledgement here to everybody involved. And I think as we have had many fruitful discussions and exchange of ideas over the past years, and that's very important. I think also there's this is a brief summary. A much more comprehensive performance comparison for the different linear colliders will be done in the framework of the Black-Low panel. So the basic limitations that was already pointed out by Chris is the beam power which you can have, and then for the luminosity also the beam strahlung which you can afford is important. If you plug it into the luminosity formula, you can say that the luminosity scales with the beam power times the square root of the beam strahlung which you can afford divided by the emittance. The square root of the emittance, I'm sorry. So, where's the challenge? It's only 4 orders of magnitude from the SLC, so, and very obviously, this has to come from both beam power, which has to go up by orders of magnitude, and beam size at the collision point, which has to go down by orders of magnitude. Actually, only 1 order of magnitude in comparison to the very successful final focus test beam experiment was done at under leadership of Slack at the SLC LINAC. And I think this was really great to get one of these 2 orders of magnitude already demonstrated. And we also will have to live with a couple of % of energy loss due to beam strahlung. And that gives us the required 4 orders of magnitude in luminosity. Okay, I skipped the efficiency. That was done by Chris in detail. Let's look at a beam strahlung in a little more detail. The beam strahlung is given by this formula here for flat beams. The smaller of the 2 sizes cancels out. The larger of the 2 remains. And now you can translate this into this is either the average energy loss, or you can also discuss this problem in terms of number of photons radiated per incoming electron. This is typically of the order of 1. And this is proportional to the ratio of charge over horizontal beam size. And the point I want to make here is that although the average energy loss due to beam strahlung is different by roughly a factor 1.5, the luminosity which is contained in the 1% peak, the 1% upper peak of the luminosity spectrum is about the same. So the reason for that is that the photons in the NLC are harder than in Tesla. That's why this is higher, but the number of photons is smaller. So if you look into this peak here, which is shown here for the case of Tesla, then Tesla and NLC are equivalent in terms of luminosity spectrum. Okay. Then what are the other limitations in principle? This is a very basic discussion. There's a lower limit on the beta function at the IP, which comes from synchrotron radiation, the quadrupoles, the so-called OIDE effect, and from the bunch lengths. This shows the OIDE effect for 500 GeV beam energy, so the upper limit of energy for the next generation machine. You can see that both NLC and Tesla are not at this limit. This gives you the beam size at the IP, including the OIDE limit. This is a beam size naively calculated by just scaling the beta function. And you can see that we are safely away from the point where the beam size doesn't decrease anymore. Great. Thank you. The other effect, this is an effect which really starts playing a role at higher energies. So it's not a negligible point, but up to 1 TeV center of mass energy does not seem to be a limitation. The hourglass effect is just the ratio of beta function, which is depth of focus, to bunch length. So if the depth of focus becomes smaller than the bunch length, you start losing. And that you can see here, the luminosity doesn't grow anymore if you try to make the beta function smaller. And these units of bunch length, the NLC beta function is smaller than for Tesla, and that explains mainly while the so-called disruption enhancement parameter is smaller for NLC than for Tesla. Frankly speaking, I don't know exactly why NLC doesn't make the beta function a little larger, but I think that's a detail. There's a side remark here, a little away from the mainstream of my talk. Everybody's used to flat beams, and everybody, I think, almost everybody thinks that's because of Beamstrahlung. I think that's not true. From the point of view of Beamstrahlung, you would rather like to make the beams round, make both emittances the same, both beta functions the same. You want to make the horizontal emittance as small as the vertical emittance. And if you do that, you get in principle a better ratio of Beamstrahlung to luminosity. And at the same time, for round beams, you get a better luminosity enhancement factor. So this is rather academic because it raises the question how to get beams which have a very small horizontal emittance. If you produce beams in damping rings, then the horizontal emittance is always much larger than the vertical. So you have to find a different way to do these beams. If you can do that, then for instance, you could do a click 3 TeV with a very low bunch charge, with round beams, same emittance in both planes, and you could get a good luminosity, slightly higher than the original design, with a slightly lower Beamstrahlung, and most important, you can practically remove the single bunch wake field effects. There are other effects and so on, but the point I want to make is if people want to think about something a little bit apart from the mainstream design of linear colliders, round beams with very small emittance in both planes and very small bunch charge is something to give a serious thought. Okay, back to the mainstream here. Next thing I want to discuss, and from now on, when I speak about emittance, I always speak about the vertical emittance in the next generation collider design, where there's a very large difference between vertical and horizontal. Okay, so vertical emittance preservation. In the main LINAC, the question is, it all comes from the transverse wake field. If the bunch goes through the structure with an offset, then there is a deflecting field which increases from the head to the tail of the bunch. This gives the bunch a banana shape and you lose luminosity. The ratio of this deflecting field to the accelerating field can be calculated for a given offset of the center, which I've chosen here to be 1 millimeter. And then this ratio, which is a measure of the perturbation of the beam, scales in the following way. It has about 2 orders of magnitude difference between Tesla and the normal conducting machines, and about 3 orders of magnitude difference if you go to click. This is a substantial difference, and this explains why the tolerances are different. It does not explain all the details of beam dynamics, so one has to look much closer, and that's what I'm going to do now. Well, some of the arguments why you cannot simply use this transverse wake field scaling to understand all differences in beam dynamics between Tesla and the NLC are listed here. First of all, an accurate alignment inside a cryostat is certainly more difficult than outside. Then some of the diagnostic equipment can have better solution in a high frequency than a low frequency machine. For instance, BPMs in a small beam pipe can be more accurate than BPMs in a large beam pipe. Effects causing emittance growth which are not or not strongly related to Linac frequency are also present. Then the high Linac repetition rate, I'll come back to that later, you will see what I mean by that, helps to cope with mechanical vibrations. Then there are limitations on the emittance, both on making a small emittance beam and preserving it from subsystems other than the main Linac. And then there are subtle differences which I'll come back to at the end of my talk. So, beam dynamics. First thing you have to assure is that there is no beam breakup. What is beam breakup? That's an instability, a collective instability, which comes from the head-to-tail defocusing effect of the wake field that can lead to exponential growth of betatron oscillation amplitudes. In order to avoid that, one applies so-called BNS damping, where one uses a correlated energy spread over the length of the bunch. In the auto-phasing condition, this cancels the wake field defocusing almost locally and almost with exactly. Then if that is the case, then a free betatron oscillation does not cause emittance growth. The BBU goes away. The remaining emittance growth is then due to uncorrelated emittance energy spread, filamentation, and non-perfect auto-phasing, which is always in practice not non-perfect, of course. So this is the precondition to operate a Linux safely and stably. That has been done. BNS has been done at the SLC Linux for many years, and it certainly works. Tesla is not in the BBU regime. With an initial Metatron oscillation of two times the beam size, which is very large, far larger than our expected orbit error, you get about a 10% emittance growth. So this is not an instability. This is something one would think to be able to afford. Nevertheless, BNS damping is very easy to implement in Tesla. You just need the first 20 GeV of the machine to impose a correlated energy spread, which you then remove. And this reduces this emittance growth by an order of magnitude. Very simple, very effective. For the NLC, you have to have 0.6% energy spread over most of the length of the Linux. Okay, so far for beam breakup. Now, another source of emittance growth comes from random uncorrelated errors, and that has to be dealt with by a method called beam-based alignment. First of all, the beam position monitors cannot be pre-aligned along a straight or better smooth line with the required accuracy. So one needs beam-based methods to achieve this accuracy later on. And I'm not going into any detail here. The point is that by all these methods, you effectively replace the BPM alignment by the BPM resolution. The BPM resolution is much better than the absolute alignment. And all these methods end up with replacing effectively the BPM alignment error by its resolution. That's the trick. In a strong wake field regime, you also have to align the accelerator structures to the orbit which has been obtained by the beam-based procedure. And that's done by the means of RF BPMs and micromovers for the NLC. So look at the tolerances for the two Linux. For Tesla, it's about a few tenths of a millimeter, and we think that we can achieve that at the time when we put the machine into the tunnel. For the NLC, this is much tighter, as you may expect, and so that requires a certain number of position monitors which tell you where the structures are, and then micromovers which allow you to move them to the beam with an accuracy of 5 to 20 micrometers. There are also differences in the required BPM resolution, and also differences in the numbers of equipment which you need. And if all this is fulfilled, then in the end, you are within your emittance growth budget, which is 50% for Tesla, but that's from damping ring to the IP and 75% for the NLC. So this is static errors. So far, if you can achieve these alignment tolerances, you can achieve your beam quality, except for perhaps other sources which are not listed here. Well, if it turns out to be difficult to achieve these, there's a plan B, and I think that's important, and also it's very efficient. This is, you can use empirical methods to further improve the beam emittance or further reduce the perturbing effects. And that's known as a wake field and dispersion correction with steering bumps. The method is shown here, for example, for Tesla. This is a simulation with randomly displaced accelerating structures. You get an emittance growth of about 10% in this particular random seed. You just turn on 2 orbit bumps along the Linux, and you reduce this by an order of magnitude. It's a little tight. Okay. For the NLC, you can do the same thing, but since there is filamentation, you have to use a certain number of emittance diagnostic stations. In Tesla, you just measure this at the end of the Linux, and so you have to use many more bumps, and you have to do that in a kind of iterative way, and eventually can also reduce your static emittance growth to something below 10% by this method. Okay. One word on multi-bunch effects. So far I've been speaking about single bunches. The message I want to get across is that from multi-bunch effects, you don't get tighter tolerances than you have to have anyway for the single bunches, provided you use structures which have detuning and damping. And this is the case for both NLC and Tesla with different methods. I don't have time to go into the details here. As you can see that the wake field drops with time and the next bunches come. It has gone down, the long-range wake field, and the only difference here is a factor of 1,000 in the strength of the wake field. Again, the static part of this perturbation can be very effectively removed. You can see here the orbit pattern which results from the long-range wake fields in Tesla, for instance. You can see inject the beam with a 1 sigma difference in orbit. It comes out with a 1 sigma difference in orbit. And the pattern of the orbit remains unchanged. That means that the induced higher order modes remain the same. And that means that you can remove this very effectively by just using a fast orbit correction feedback, where you program this pattern in a feed-forward table, and then it's gone, and it will remain gone. Okay, so far for the static effects. Now I come to this question of stability. Ground motion is an important point here. So let's say a few words on ground motion. For Tesla, we derived the ground motion model from data which we took at Hera. In summary, it says that at frequencies which are relevant here, at about 1 Hz and above, the RMS amplitude is about 70 nanometers, and it's essentially uncorrelated. It means if you measure 2 points by like 10 meters apart or so, then there is hardly any correlation at this frequency. Large amplitudes at lower frequency, you can see this goes up here to microns, are not critical because, first of all, they have a large wavelength and also they have a strong correlation. This is known as a microseismic peak. This increase here is known as microseismic peak, and it's supposed to come mainly from ocean waves. So the DAISY site is considered a noisy site. Let me explain why. This is the Hera ring in Hamburg-Bahrenfeld. It's about 15 meters underground. You can see that there's a 6-lane highway going by very closely. There are a couple of 4-lane major roads with heavy traffic, also this one, partially even going over the Hera tunnel. So this is certainly any ground motion model which is derived from the conditions in this storage ring here is certainly pessimistic and upper limit, and we feel quite confident if we can live with that for Tesla, then in the end it's going to be better, because the main part of the Tesla lineup would be out in the country, whereas nothing of this sort here. So that's just for those of you who don't know that the DAISY site and the entire Hera ring is just 5 miles from the downtown of a 2 million inhabitant city of Hamburg. At SLAC, measurements have been done in the Linac tunnel and in the SLD pit. It's interesting to note that the correlation versus frequency is similar as at Hera, but the amplitudes are smaller by more than order of magnitude. So there's also this microseismic peak here, but it's strongly correlated and so on. So it's not that different except for the scale. And it must have to do with the conditions of the ground. I think it's clear. So this is where the SLAC colleagues derived the model for the NLC from. Amplitudes are very small, but they also did measurements in the SLD pit. You can see that the amplitudes there can be quite a bit higher, especially if you switch on part of the equipment. So this tells us one has to be very careful that a quiet site is a good thing to have, but you have to be very careful to make sure that it remains quiet once you occupy it. There is a long-term effect known as slow diffusive ground motion, is expressed normally by the so-called ATL rule. From the Hera model, where we measured orbit drift in Hera on a scale from minutes to weeks, we derived this number. From the SLAC measurements, the number is about an order of magnitude smaller. But take into account this is the mean square of the motion, so the amplitudes are a factor of 3 smaller. The difference on the long-term motion is much less than the difference on the faster vibration. Okay, so taking all this together, this is what we expect for the machine, for the different models and the different machines. One has to compare with the tolerance For Tesla, we remain within the tolerances, even with our pessimistic or very conservative model. For NLC, it would get tight. With the Hera model, it would get rather tight, probably a little too tight. Whereas with the Slack model, everything is fine. One should also take into account that temperature drifts, time-varying stray fields, and other sources may not at all be negligible, especially if you look at the more quiet conditions. I think then it's very easy to have things of that sort which exceed the effects of ground motion quite a bit. Okay, finally, the stability of the final focus is, of course, an issue at the nanometer spot size level. You can see that the difference in the spot size is not that large, about a factor of 2. There is a big difference in the bunch spacing that allows Tesla to do rather easily orbit correction on a bunch-to-bunch level. This is quite a bit more challenging for the NLC. Also, the energy spread in Tesla is smaller, and that helps a little bit to stabilize the beam. Luminosity stability, there are 2 definitions here. One is called the jitter stability tolerance, and the other is the drift stability tolerance. Jitter means just steering at the IP, just the beams missing each other. Drift means increase of the spot size due to dispersive effects and betatron coupling. And of course, the jitter is much more sensitive than the drift. So the full bars here are jitter, the open bars are drift tolerances. This is for the NLC final focus system. It's a little different for Tesla. It's a little more relaxed, but it's not a big factor. And this is the inverse of the tolerance. So this is 1 nanometer. This is 1 micrometer. So you can see the final doublet here as a tolerance at a little below 1 nanometer, which is just met by the quiet ground motion model of Slack. It's not met if you look into the SLD pit with equipment on. The Tesla approach to deal with this is to stabilize the orbit at the IP within a tenth of a sigma in angle and offset with the 3 megahertz intra-train feedback based on the large bunch spacing of 330 nanoseconds. Then we would like to have active stabilization of some of the supports in case we really have this high 70 nanometer vibration, because it would start to cause us a little spot size dilution from dispersion. So this was demonstrated about 10 years ago, 8 years ago at the S-Bahn test facility at DAISY. This is easy. This costs about $5,000 US. And that gives us an order of magnitude for this effect. So I think it would be wise to put those stabilized supports in. And then we can maintain the spot size within a few % with a slow orbit correction feedback. Luminosity tuning can be done by scanning orthogonal knobs within a single bunch train. That's very nice. A single bunch train about once a day. This is something which doesn't really affect the luminosity operation efficiency. And the C approach is that you get a sufficient orbit stability at the IP with a pulse-to-pulse orbit feedback if you can rely on the small ground motion amplitudes measured in the SLC tunnel. It's fine. So as I said, there is a plan B where you can actively stabilize final doublet, or also use a very fast, quite challenging IP steering feedback. To maintain the spot size on a pulse-to-pulse basis is relatively easy for the NLC because of the higher repetition rate. The 120 Hertz repetition rate in comparison to the 5 Hertz for Tesla makes up for more than the difference in beam energy spread. So it's easier. And luminosity tuning can be done similar as for Tesla, but one would probably need to do that on a pulse-to-pulse and not on a single bunch train basis. Okay, this is our steering feedback. I'm running out of time, so I keep on going and come to the last part here. This is a quite interesting effect. It's very nice for accelerator physics, not so nice for the Tesla collider. It's a so-called kink instability effect. the first paper I found on this is written by Chin in 1987. It's actually a DAISY report. It's analysis of a two-stream instability which leads to exponential growth of oscillation amplitudes for bunches colliding with an offset. And this is a linear theory, somewhat simplified. You can see that there is an exponential growth of the initial offset y0, and the growth rate scales with the square root of the disruption parameter. This is an important point here. Square root of the disruption parameter. So with a large disruption parameter, this means you have tighter tolerances on the IP steering. That's understandable because an initial error is amplified. That we knew for a long time, and that was obvious, but there is an even more annoying effect, and that is the so-called banana effect, and that means that not only an offset of the bunches, but also an eternal deformation of the bunches with zero average offset leads to an exponential growth. And this is hopefully now an animated beam simulation here. You can see that there is a growing coherent mode of the colliding bunches. The left is a 3D version, so you can see the two sheets of paper which are colliding there. And the right is just the vertical projection. And you can hardly see the initial deformation. This is really, I mean, you can just see that there's a tiny little shape on the bunch, but it's almost invisible. This is a fifth of the sigma. The RMS amplitude of this deformation is 1/5 of a beam sigma, so it's hardly visible. And you can see that it grows substantially during collision. Not nice. So the effect of that is that the luminosity is more sensitive to correlated admittance growth. This deformation is a correlated admittance growth. It's a YZ or Y prime Z effect. And if you do that for many random seeds of Dirac perturbations and so on, you can calculate the expected luminosity as a function of this correlated admittance growth, and that's calculated here for Tesla with other reasonable assumptions, which I'm not going to go into. And you can see that even for 1% admittance growth, you get a 15% reduction in luminosity, whereas you would expect 0.5%. So this effect enhances the luminosity loss for small admittance growth by a factor of 30. This, the dashed line here is what you would expect if this admittance growth was uncorrelated, hardly visible. Well, fortunately, the feedback helps a little bit. Why is that? Well, the feedback only detects relative bunch offsets. I'm sorry. The feedback detects deflections at the IP. And the feedback doesn't know where they come from. It just sees that the bunches have a net deflection when coming from the IP. And it turns out that with this banana effect, the bunches do have net deflections, and that depends on the relative phase and shape of the distortion. But the feedback will just steer the beams as if these deflections were due to an offset at the IP. Okay? And fortunately, that systematically increases the luminosity. It's not, I don't think this is I don't think that was clear from the beginning that it would do that. But okay, it does it. So it gets a little better, but the effect remains strong. Okay, what would one do? We could shorten the bunch by a factor of 2, then we get a disruption parameter like the NLC, so the effects would be first sight about the same and would be reduced. On the other hand, the question is, since we can stabilize our emittance growth, you can tune away the static part, you can stabilize the emittance growth within the 1-2% level, and whether you want to go from here to make sure you get your design luminosity within something like 10% is, to my mind, a little questionable. I personally think that since you only encounter this problem when you get close to your design luminosity, I wouldn't worry too much about it. But that's my personal opinion. I mean, this effect in the initial running of the machine, when you are not going to have the design emittances, that's my opinion too, then you don't have to worry about that effect. And at the time when this effect plays a role, to limit your performance, then this project will have been a success. Okay, this is really a detail, but it's going to be interesting to discuss it further with our colleagues at SLAC in more detail. If we go the two shorter bunches, we have the same disruption parameter as the NLC. Still, it looks like the NLC bunches are somewhat less sensitive to this effect than the Tesla bunches. And why is that? Well, look at the YZ correlation for a typical bunch coming out from the NLC linear. This looks more like an albatross than a banana, which means that the wavelength of the perturbation in units of bunch length is shorter. And that seems to, looks like it makes this kink instability somewhat less sensitive. But this certainly has to be looked at in more detail. For sure, all the dispersive aberrations which come from the beam delivery system, which are entirely correlated for the NLC, they look the same as the correlated bunch deformation in Tesla. So they will suffer from this effect. So the tolerances on the NLC final focus system are more tight than the people think so far. Okay. Conclusion. The luminosity goals for both Tesla and NLC are an upper limit. I think they are a reasonable upper limit, but they are an upper limit. Don't push us further. Achieving the same value for, say, the NLC design value, which is lower than the Tesla design value, I believe is very likely easier for Tesla. And it's very hard to beat the efficiency, which is a factor 2.5. And I also think that one cannot say that, that it's more difficult in Tesla to preserve the emittance than in the NLC LINAC. Beam dynamics in strong wake field regime, nevertheless, are very well understood. I think our colleagues working on the high-frequency LINACs have done a terrific job in the past 12, 15 years on that. It's great, and it's very well understood. The methods are very well defined, which have to be applied to guarantee the beam quality and so on. It's clear that the complexity and the required accuracy of the diagnostics and correction equipment is substantially more demanding than for Tesla. There's no doubt about it, which doesn't mean that it doesn't work. The higher repetition rate is a plus for the NLC with regard to spot size stabilization in the final focus system. Okay, thanks.
One crucial question. One crucial question.
Density is obviously one issue.
Yes. Yeah, I'm sorry. Yeah, the damping ring is a big issue. I forgot to say one of my early transparencies when I had the generation and the preservation of the emittance. I forgot to say that I'm going to speak only about the preservation of the emittance in some detail, because otherwise I would have overloaded my talk, which was apparently overloaded anyway. So the damping ring, not only the damping ring, but damping ring bunch compressors, other subjects are important, of course, and have to be compared as well. You're right. But I don't have time to do that now. We can do that later. But
Okay, well, we've got a question and answer session coming up at the end here. So why don't we go ahead and hear Tom Markevich talk about IP design.